Thank you, Dennis. Thank you for a nice introduction. Yeah, we met in the train. It was ICE to Amsterdam, so I was changing normally in that time in Utrecht. So yeah, that's the story. Okay. So I will talk about the very recent work. This is the work with Taras Bodnar. We work a lot of in the high-dimensional statistics and random matrix theory. This is one of the works which is, I think, quite fundamental because it has a lot of applications. I will try first to introduce you the theory that is behind this, and then a few applications. I think it's not a few, but can be more, I would say. So first, for some people who don't know exactly what is happening in high dimensions, I'll do a short introduction about the curse of dimensionality in high-dimensional statistics. Then I will talk about the main theoretical results we showed for generalized inverses. So it's about Moore-Penrose inverse, Ridge-type inverses, and actually, yeah, you can show with this technology many asymptotic results for even other inverse matrices. But I think those two are most important. And applications of those results I show you in the shrinkage estimation and precision matrix, in portfolio theory, regularization, for example, and the high order nonlinear shrinkage. So potentially, I will show you that you can actually also estimate nonlinear shrinkage estimator or construct the bona fide nonlinear shrinkage estimator with this methodology. All right, so what is the setup? The setup is quite easy, but before I go to the setup of the paper, I will show you a simple example from the statistics. So you have an observation matrix, which is p-dimensional, based on the p-dimensional random vectors. So you have n vectors, you stick them together, have a big observation matrix, and we assume that the covariance matrix of this xi is sigma, the mean is 0, for example, and yeah, most people are interested in the sigma itself, in the covariance matrix. Sometimes we also need the eigenvalues of this matrix if you want to do PCA and other nice things. And what you do in practice, you replace it by the sample covariance. Most of the times you're happy, but in the high-dimensional statistics, you're not. I will show you in a few seconds why you're not. All right, so why you're happy in the classical statistics, just because in the classical theory, if you fix dimension and send the sample size to infinity, you have entry-wise strong law of large numbers, you know the Sn, the simple covariance is converging to sigma, but also you have that the maximum eigenvalue of the Sn converges to the maximum eigenvalue of the population counterpart, and many other things, because any functional of Sn will converge to the same functional of the truth, right? So this is something we know, right? So this is happening not only with covariance matrix. Okay, but in the high dimensions, the thing is different, and random matrix theory is actually dealing with the case when dimension and sample size together grow to infinity, but there is sort of balance, so the dimension and sample size in ratio keep constant. So what we know there, simplest examples, if I take sigma to equal to identity, I can already see that the maximum eigenvalue is not converging to 1. It should be 1, right? Because the true maximum eigenvalue is 1. But it's converging to 1 plus square root of c squared. And c is this ratio, dimension over sample size. So there is no consistency already in this very simple case. Moreover, if you think, okay, maybe I take Frobenius norm of the difference, sample covariance and identity, because identity is now true covariance matrix, right? And divide by dimension, hoping that maybe this is converging to 0, but it's not. Now we already showed this with Taras one time ago. It's a constant c, almost surely. So it's dimension over the sample size. So even in this case, you cannot hope for consistency in the high-dimensional simple regime. Right, why this is happening? Yeah, there are many reasons, because yeah, you have infinitely many elements at some point, so you have, instead of finite sums, infinite sums. So it could diverge, it could even converge, but not to 0. So there are many reasons for that, but actually one of the reasons is that the matrix norms are not equivalent in the high dimensions. So if you take the maximum eigenvalue, you can always bound it by this inequality, its maximum value of A, and P by the maximum value of A. And you see already that this bound is loose if the dimension goes to infinity already here. Or if you take the Frobenius norm, right, you can also see that the Frobenius norm itself is always greater than or equal to 0, but the maximum eigenvalue of the difference is not going to be 0 into the limit. So that's the problem. That's which is called curse of dimensionality. We cannot rely on the sample estimates. That's the main message. So something else should be done. And there are many things done in the literature. In this specific talk, I will concentrate on very focused case on the inverse problems. But anyway, what is known now in general? It's known that even so, it's not converging. You see, there is specific pattern. It's converging to something dependent on C, and there is specific pattern. You can show it, and firstly shown by Marchenko-Faster in 1967. So if you take the spectral measure, this is basically the cumulative distribution function of eigenvalues of the sample covariance. Then you can show that it is converging almost surely to these density, which has, of course, discrete part and continuous part, because depending if P is greater or smaller than N, you will have different situations. And this density, by the way, is called Marchenko-Faster density. Lambda plus is the largest eigenvalue, lambda minus is the negative eigenvalue. If you plot this, it looks like that. So you you don't have enough concentration around 1, but you have some law around 1, which is called Marchenko-Faster law. This is just for you to see the difference. Okay, this is finite sample, sort of small sample, Marchenko-Faster law that you could see if you don't have enough dimension sample size. If you increase Pn, you'll see this very nicely shaped density, which is called Marchenko-Faster density. Okay, so this is maybe very basics from random matrix theory, because this Marchenko-Faster law plays a role in the theory I do, like central limit theorem or low flux numbers say. Okay, so it's very, very important thing. All right. But in many applications, you don't only need to know what eigenvalues are doing, you also need to know what the eigenvectors are doing together with them. And the behavior that is different in small, large dimensions. So what we observe is that our intuition is not in line anymore with what we expect, what is in the nature, in the real life. In high dimensional problems, your sample estimator is not reliable, so you should do always or mostly something else. In linear models, and what I call linear models is covariance, precision matrix estimation, spectral clustering, least squares regression, the small dimensional intuition is not valid anymore already. But the same problem also goes into nonlinear models like kernel spectral clustering, nonlinear neural nets. Yeah, if you have problem already on the linear level, they go further to the other levels as well. So technical challenges is the classical RMT focuses only on eigenvalue distributions. But the machine learning financial applications, they need behavioral eigenvectors. So more complex matrix functionals. All right. Okay, this is the introduction. Let's go to the topic. So now what I focus on with Saras in the work is the precision or inverse covariance matrix estimation, basically. To do this, we develop a specific theory. So let's show you the setup of the problem. So we concentrate on the inverse directly, not just looking on sigma and then inverting it. Yeah, you can always construct, there are plenty of estimators now and then invert it, but we want to target sigma minus 1. All right, a lot of applications, but again, what you do, you should work somehow with sample estimate and try to make it better. The problem with the precision matrix, if you take the sample estimator, it is singular in the case dimension is greater than the sample size, so it's already useless. You cannot invert it in the usual way, right? But still, you need to estimate sigma to the power minus 1. So we propose in this work 3 estimators, but I think with this methodology you can also do more. Yeah, you can look on more specific matrices. We look first on Moore-Penrose inverse, which is, I think it has a long history, right? It's the unique inverse which satisfies these four properties, and this is really generalized inverse, right? So potentially, and from the SVD point of view, you just invert non-zero eigenvalues and you keep zeros. That's what it does, right? So it's quite easy to compute, very fast. It has sometimes even closed form expressions if p is greater than n, which is of course an advantage. And it's used everywhere, some linear systems, smallest known solutions, but itself, it is useless in high dimensions as well. So yeah, you cannot use it just hoping that it will work. Same with Tikhonov. Tikhonov regularization, also known as Ridge in the regression setting. What you do, okay, you add the positive constant to any eigenvalue, and then you can invert it. So very easy, but it is also used everywhere. In fact, it is always well posed. It is some sense bias variance trade-off, because the larger is the penalty t, the more you bias your estimator, right? But the smaller is the variance. So it's somehow the challenge to find the best t for this type of inverse, right? It's very well known in ridge regression and some ML problems as well. All right, but still this one is also useless if you don't know the optimal t value. So it will work, you can invert it, all right. You can also invert this one. This one's even easier. And we looked also on the third one, which is some sort of mutant of this two. Let me explain you why. Because this matrix here, which we call S plus minus, so it's S plus, Moore-Penrose, S minus is ridge, and S plus minus is sort of, the sum of both, or maybe a total, I don't know. Why? Because if you send here in this expression the small t to 0, you land on Moore-Penrose. Right? If you don't do it, you can always write the S plus minus as ridge part plus something else. So it is sort of having properties of both in some sense. But it has also another nice interpretation we will see further in the slides. So why this matrix is interesting to look on? Yeah, if your P over N ratio is close to 1, then this matrix will be the better choice to look on. Otherwise, actually, Moore-Penrose and Tikhonov ridge regularization will be working very, very closely to each other. All right. So what we are looking on? We are looking on the, as I said, specific functionals, but we don't only look on eigenvalues. So these S plus, S minus, S plus minus, I put it as this hashtag. So it's either the three, right? And I multiply this matrix to the power m. So I'm looking for sort of m moments multiplied by some matrix theta and taking a trace of it. So what is that actually? It's empirical weighted moments of the specific inverse, either Moore-Penrose or ridge or mutant. Moore-Penrose ridge, we call it. So it's looking, okay, what that brings. That brings a lot, actually, because in random matrix theory, theta is 1 over p multiplied by identity. And if you take specific thetas, you will get very, very interesting results. For example, so again, 1 over p is classical old school random matrix theory. It's called still Ph transformation if you take theta in this form. And this is just empirical moment, nothing special. If you take theta as the product of two vectors, either equal or non-equal ones, you study quadratic forms or bilinear forms of that logic. And that involves eigenvectors automatically. So this I call new school RMT. And if you take theta as some function of sigma normalized by dimension, these are so-called Laplace functionals. And they are, this is the building block from nonlinear shrinkage formula. So for specific theta, you cover a lot of interesting cases. For example, you can also take theta equal to the product of two unit vectors, EI, EJ, and you recover the asymptotic of the entries of the matrix. So you can do a lot of things. This is the matrix. Okay, this is here, right? This reveals information of the eigenvectors, but most importantly, these things deliver us the way to construct shrinkage estimators when P is greater than N. Yeah, was actually the main aim to look on that. Yes. Right, in the literature, to be honest, we didn't find a lot. So 3 papers. One of them, my author was actually as well. Yeah. So mostly relying on either you have normality assumption, fixed dimensions, or you assume that sigma is identity. So yeah, not a lot of things. And I think Moore-Penrose case is the most interesting case to consider. So what we look on, this is the data generating model. Very simple one. So the observation matrix contains the vector mu as the overall mean. So you have the IID random vectors. It contains sigma as covariance matrix, and matrix X is here. It just means the noise matrix, basically. So the X is generating the noise. And it consists of IID random variables, so 0 mean unit variances. Most importantly, we don't need anything more except the force moment, force plus a bit moment. Sigma here, the covariance matrix, has uniformly bounded spectra. Actually, the largest eigenvalue is bounded away from infinity, and also the smallest one, in some cases, should be bounded away from 0, but in general, not always. And this translating matrix theta, what we assume is if it's of finite rank, then it could be written in this form. Then we assume that those vectors here have finite Euclidean norm. If it's a full rank, then its maximum eigenvalue goes to 0. It's quite general because you can put a lot of things inside. So 1 over P identity is just very, very trivial example of that setup. And actually in the estimators we have, you can always normalize theta to fulfill this, because very easy. Do I have this by the way? No, because the property which is easier to check is this too. It's a bit more restrictive, it's easier to check. The trace of theta should be bounded. So if trace of theta is bounded, this is fulfilled. Yeah, so that's what you can have in mind. Right, is it clear what's happening? Okay. Now, not nice formulas come in because those moments we realized that can be presented using the partial exponential Bell polynomials. I don't know if you know them. I didn't know them before as well when we started working on the paper. But they look like that. Yeah, they are partial because you take a part. Yeah, you take n minus k plus 1, you take a part, not all sequence. And this is the sum, basically. Looks a bit horrible. Seems like it's not easy to compute, but actually there is very nice package in R, which is called K-statistics. With a paper published in Bernoulli by Dinardo et al. They actually showed how to compute these type of polynomials very, very fast and efficiently. So potentially you can compute anything with them as you wish. Here is just a few examples how the polynomials look like with different values of m and k, just for you to have the idea. But it doesn't matter so much. This, yeah, you can compute for any k. Right? Now, if I take Moore-Penrose inverse, assuming the A1, A3, A2, A3 are true, then we can show that the weighted tracial moment of the Moore-Penrose is converging, or it's behaving asymptotically exactly the same as specific Sm of theta, deterministic sequence, which is looking like that. It's the weighted sum, weighted by these Bell polynomials, basically, of specific dk theta, which have these expression. Looks ugly, but if you take m equal 1, you will see what is happening. Because if you take m equal 1, so basically k equal 1 here, you see that the Moore-Penrose inverse, in fact, behaves asymptotically as this matrix. Which is, you remember? Let me go back. Come on. This one. Yeah, very closely related to this one. That's why we took it, actually. So it behaves as specific regularizer of the sigma asymptotically. So this is what Moore-Penrose matrix is doing. right? The function v is vital. I will not stand a lot of this function. I will tell you if you ask me or in the break, but it is unique solution of specific equation, and all of the other vk's are actually the derivatives which you can recursively compute. If there is a recursive formula, we go to them, so you can compute them. So the first question, which could be, okay, can I estimate this v? It already will be very useful, right? But before we just computed 4 moments, so you see how they look like. They're not so scary as the general formula, but you can always, you can compute by hand. It's something special. And you see these d1, d2, they're all involved. So every moment depends on the previous moment. So you have sort of recursion inside, right? It's not converging to something you want. It should converge to the trace of sigma to the power minus 1 theta. Yeah, I'm sorry, it's not. It's not. But yeah, actually, if you put if c goes to even if c goes to 0, you can't, right? Because the asymptotics is different. It's greater than 1. All right, how to estimate those derivatives? Especially if you take the classical RMT case with theta equal to 1 over b identity, it seems to be it's a special case. You get specific formula which depends only on those derivatives at point 0. But this is here basically just the empirical moment. So I can estimate all of them divided by 1 minus 1 to the power minus m, multiplied by n minus 1 factorial, multiplied by cn, and I have consistent estimate. So, which is purely data driven. So I don't need to solve even this crazy equation. I find v, so first I need to estimate this equation consistently and then solve it numerically. What I need to do, I just need to take this, and this will automatically converge to what I need. All right. So this is just to show you that I'm not lying. This is converging. This is working. The estimators are converging. They're very close. Depending, of course, I took the green line as the n equal 100, and then you have these dotted line 250 and blue line 500, and of course you take more and more n, it becomes closer and closer because I took ratio should be closer to 1. Right? And it seems to be, interestingly, the larger is dimension over sample size ratio, the faster they converge. Right? Okay, so the same you can do with Stephanov, with Ridge. You get the same ugly, not the same, you get the ugly formula, I agree. Interestingly enough, you have here very, very, very similar expression. But now you have not v at 0, but you have the same function v at point t. It's the same function, but at point t, it satisfies just a bit different equation. But at point 0, this equation coincides with that. Oh, sorry. With that. So with Ridge, you can do the same. You can do the trick and estimate those functions v consistently. Now it depends on regularization parameter. Of course, t is the penalty, right? I didn't tell you how to find optimal t because I didn't go to the application section right now, but I will show you in a few seconds. Right, more interesting section are applications. So we tried first the following. We said, okay, let's do shrinkage, and we've done shrinkage before. So let's shrink those inverses. That means take the linear combination of the sample inverse we like and some target matrix P0. Most of the applications, I took identity because I wanted to compare with the Wolf estimator. But you can take any matrix P0. We took the convenience norm. So this is the difference between the product P hat is generic estimator of this form, multiplied by sigma minus identity. So, and of course, if this is small, then it's clear that P hat becomes small, closer and closer to the inverse, right? So it's quite classical inverse quadratic loss function, by the way. You can take other one. So it's not something which is tailored to this loss function. And if you take derivatives over alpha beta, which is quadratic, it's convex problem, by the way. you see the optimal alpha betas, they look like that. And these green things are nothing else as weighted sample moments, the things we derived before. So if I can find estimators of these objects, I can estimate, I can build a shrinkage estimate. And it's done in 2 steps. I look on the limits of those, and then I estimate the limits consistently. So I look on the limits of those. I know the limits, right, already. Then I estimate the limits. And actually everything is dependent on this V0, Vt functions. All right. And don't worry about theta. You see, I can always self-normalize. I can divide here by 1 by p and other things so that the condition on theta is fulfilled. It's not the problem at all to have a trace bounded, right? All right. So what is nice with quadratic loss functions is that you can build a full square. So I can build a full square in alpha and in beta, and I get the rest. And it seems to be if I build the full square here, these functions C1, C2 are independent on alpha beta, they're positive. So the rest is here a constant plus this function, which is only dependent on the penalty. So now what I've done, I separated 2 problems: shrinkage, simple shrinkage problem, and penalty estimation or penalty optimization in this simple form. Because if I take alpha equal to alpha star, beta equal to beta star, this is the minimum, so it's 0. So I just need to minimize this function or maximize the minus function, so I need to maximize this function over t only. So I have sort of advantage taking this loss function. Yeah, I agree in this case. But okay, that's the illustration. I can find the limit of this guy, estimate the limit consistently, and then optimize the limit over t. This is my optimal penalty. That's what we have done. And this is really out of sample optimal in case t lives in the complex interval, because if you remember calculus, because it's only an optimization, it should be uniform convergence with respect to t. Yeah, then I know I'm targeting my estimated variance of it, or the optimal value of the estimated variance will converge to the true optimal value. So if t is in complex interval, you will be safe. Otherwise, on some edges, for example, by ridge, the edge will be 0, right? So if you're close to 0, you'll get the problems. But not by the mutant value. Mutant one has no problems at 0. All right. Having the theory, I can estimate all of those small parts inside of the shrinkage intensities consistently. So these objects, even if you see dependence and sequence, these objects are all in closed form data-driven purely. So they converge to what you need. Yeah, these 2, alpha hat and beta hat, have the same asymptotic limits as those one. And this is just the illustration for the case of Moore-Penrose, but we have the same for Ridge and for other inverses. All right, so I can compare now with benchmarks, right? You don't see anything, but I will explain. So we took the trial, which is the things that I both like very much. We like them as well. Not them, but the trial. Okay, it's just the measure of the fit. So if you look carefully, what is that? It's our loss function divided by the one where you plug in like the traditional estimator. We took traditional as the Moore-Penrose itself, non-shrunk version of it. And if you take 1 minus, you see that your logic should be inverted. So the higher is the value, the better. Yeah, then 100% is sigma to the power minus 1. And if you have Sn plus, then it's 0, right? So it's relative improvement over Moore-Penrose inverse. Let's call it in this way, right? This line, as you cannot see, is the well-known nonlinear shrinkage estimator. The bona fide, the one they use always, it works. It's worse here in this case because it is optimized for the sigma, not sigma minus 1. So it's not something that should be something which is boundary in this case. But the others, they are here, and the solid blue line is the best you can do. There exists the nonlinear oracle shrinkage, which is the best one, because I took P0 equal to identity. So now I shrink eigenvalues. So it's equivariant estimator. If you know the theory and you know that there exists this line. So I know this is the best I can do in some sense. And they are all very, very tight on there. With the Moore-Penrose, maybe slightly worse, but I mean, I don't know how much percent, maybe 0 points. They need to zoom in, right, to see very carefully. This one is the empirical bias baseline. All right, for different values of C, so it's quite stable, and it even goes up a bit, strangely, if you increase C. Of course, if you can, or if you could, estimate the blue line consistently by the Drouin-Wolf procedure, you will get the Drouin-Wolf estimator, right? But they didn't do it because it's not elementary for that setup. You should do something else. For these estimators, it was easy. But I think with this methodology, you can estimate all of them. Yeah, you just need to change loss function, you'll get a different estimate. So there is sort of universality in that result. I still have time. Okay. Few applications. I like portfolios. I don't know who knows me. I like financial applications. I never invested my money, by the way, by myself. But I can do some fancy stuff with this. So if you apply this theory to portfolio optimization, you can apply for, you see, this is penalized global minimum variance portfolio. We minimize the variance by bounding the Euclidean norm of the weights, portfolio weights. So the money you put on the assets. And the solution is well known. This is sort of regularized version of the global minimum variance portfolio, which is bad. I mean, we know that. So we propose to shrink it to the target, which is any target portfolio. And here is the regularized version. But now what we can do with this methodology, we can estimate psi and lambda in out of sample regime consistently. So that's the advantage. The same trick, by the way, it's quadratic. So you can open the square, you can have one part which gives you psi as a function of lambda, and another part purely function of lambda. So you optimize picking psi equal to psi star, have 0, and you need to minimize minus L of lambda, which is function of lambda solving. The same trick. This is how this function L actually looks like. And we actually done the case here. C is smaller than 1. For this specific example, we done it. So you have this function. It looks. This is the true value, the oracle, so asymptotic value, and the estimated, purely data-driven. So they are very close, and the true lambda is really picked nicely. If P is greater than N, it's also good, but there is here a small problem. And this is something about uniform convergence I mentioned here. On the edge, if lambda here becomes closer to 1, it's lambda 1 minus lambda. If lambda becomes closer to 1, this guy is singular, so it's jumps. You should be careful. This is estimated. But if you numerically take here an epsilon away from the edge, it will work on the grid. All right. Yeah, a nice example why cross-validation will not work in high dimensions. For this example, and actually for other examples as well. If you do cross-validation, you can imagine P and N are comparable. If you now split N in smaller parts, come on, you really think you will estimate lambda consistently? It's impossible by cross-validation. And if you do it here, you see this one is this cross-validated estimates of lambda. Maybe very plainly, I didn't thought a lot about this. Maybe you can do a shift of it, but it's very much biased, by the way, to the right. The green one is the data-driven estimator. The blue one is the true, basically. So it's oracle minus true, bona fide minus true, cross-validation minus true, and we want them to fluctuate around 0 and not around something else. So cross-validation will not work, but this procedure works without taking, test data, validation data, whatever. You just have a data set and you do it at once in one data set. Right. This is an empirical example. I don't like this long tables, but this is just to convince you that the double shrinkage, we call it in the paper, by the way, because you shrink 2 times basically. The matrix and the weight double shrinkage works very good. Looking on a lot of measures with a small turnover, if you know what is that from financial literature, and it beats the going wood. This example quite well. Yeah, we took 2 different targets. Of course, you can play a bit around this target in these estimators, but you can do quite well. Yeah, I just added this sitting in my sitting in the office of Dennis. I thought, okay, why? Maybe somebody will ask why you didn't do Moore-Penrose GMV portfolio. I did. I did Moore-Penrose. It has this form, which looks very nice, but if you look carefully how they look here, they are very ugly. Anyway, but this is data-driven estimator of the shrinkage intensity. I can use it. And it's not optimizing the penalty. It's estimating penalty together automatically, right? What is the advantage? It's an order or 2 orders faster than regularization. 5 minutes, yes. Because if you optimize the nonlinear function, you can imagine in high dimensions that will take some time. And if you get even in troubles with uniform conversions, that could be that you pick sometimes a bad lambda because there could be 2 peaks or something like that, right? Right, this is just to show you, this is the relative auto-sample variance. What we see here is the green line is our old paper from 2018, where we solved the situation only for small values of C, so it's approximation of the Moore-Penrose, which is not exact. Today we have the exact value, and you see for small values, they are very close. So we really, this is in line with what we have been doing before, but then they depart. So the green line and this blue C1 line, they depart. And of course, the smaller the better because it's variance. And these dotted red line is ridge. Ridge is better. Yes, ridge is better, but you pay for that as well because you have additional computational time for your penalty. So, but in the end, after some C, they become very close. So it is, if it's worse to pay for that, this is user problem, I think. Right? So I think Moore-Penrose, shrunk version of Moore-Penrose, is very much reflecting nonlinear shrinkage. If you look on nonlinear shrinkage formula, very new one they published in 2020 in Bernoulli, this is sort of shrinking Moore-Penrose inverse, very closely related to that. And the last one, I said I can give you a lot of examples, but this one I like because what you can say, I just take any function of my inverse, analytic function, say, okay, it's a very smooth, nice function, and I approximate it as Taylor expansion to some other m. Those are moments, right? And if I do this, I get this expression. So this is the m's Taylor expansion or approximation, where if you expand same points, those functions, d0, say, you will have the shrinkage of the moment to the identity, by the way. So here you have, instead of just alpha by Sn hashtag plus alpha 0 by identity, you have the whole bunch of moments of that inverse, because you approximate unknown function, right? And you take the same loss, but now I have here the vector of alphas to optimize over. I can do the same thing I showed you before. I skipped it because it's a big mess. But you can estimate those alphas consistently. And just to show you the last picture. So this is the best you can do. The nonlinear shrinkage oracle. This is Moore-Penrose. And now I increase n. Without paying anything more. I'm not paying more on dimensional sample size. I just increase n m. I have more and more moments. I approach to the unknown line. I don't know the function, but this procedure automatically learns it. Yeah, it's now trying to say learns it. It actually estimates. Okay, this is based on these 2 works. Mostly, I'm very thankful for your attention and comments.